Hello and welcome. This is an ideal reheat Rankine cycle. So let's first go over the schematic of the cycle and how it is translated to the TS diagram before we go out and solve the problem. So let's say we begin from state 1. In this case, 1 to 2 is the isentropic pump. So at state 1, the pressure must be on the pressure of the condenser side. So I'm calling it P equal PC. And the job of the pump is to raise the pressure from pressure of the condenser to the pressure of the boiler. We are calling it P equals PB. And they are given here. This is the pressure of the boiler, and this is the pressure of the condenser. From state 2, it is heated in the boiler to the maximum temperature at T3, and it's here, 620 degrees Celsius. And then it expands from 3 to 4 in an isentropic turbine. And about state 4, the reheat pressure is not given. In fact, we are asked to find the reheat pressure. That makes the problem a little more difficult. And then from state 4, it's reheated. It's an ideal cycle, so the reheat temperature is same as the maximum temperature. So temperature 3 and 5 are assumed equal. And then finally, the moisture content in the exit of the turbine, the second turbine, so reheating is done from 4 to 5. So we are adding, if we have to draw arrows to show where the heat is added, first from 2 to 3, there's a boiler, and then heat is also added in the reheat zone. And then from 5 to 6, we have the second low pressure turbine. So 5 to 6 again is isentropic, and is given the condition at the exit is that not to exceed 10% moisture content, which means the quality there can be at the 90%, cannot be below 90%, because if quality is below 90%, then moisture content will be more than 10%. So basically the quality is given as 90%. So this is the closure of the problem. So for state 6 now we know the quality is 0.9. So that will help us, because if you know the quality at state 6, we can figure out state 6. 5 is isentropic to state 6, so 5 can be found. And once we know state 5, we know the reheat pressure. And the entire cycle is then solved. So one more thing, the mass flow rate is not given in this problem, so we'll just assume 1 kg per second, because the mass flow rate is not going to change the answer that is sought in the problem. Okay, so let's go. I've already solved to reduce the demands for, to reduce the video time. I have already solved the problem, and I'm just going to go over what I have done to make sure I take you through every step. First thing I did is isolate the variables, important variables here, so that we can later change if you want and do a parametric study. So the boiler pressure, I just call it PB, 15,000. In SI units is kPa. This is the boiler pressure. Maximum temperature again should be in Kelvin, because it should be in SI units. This is the condenser pressure. And the turbine exit, I'm just call it X exit. So these are my special variable declared. If you go to the state panel, let's start from state 1. So as you can see, state 1 is the pump inlet. So pressure is same as condenser pressure. And as you can see, the quality is 0, and the mass flow rate I set to 1 kg per second. So therefore, these three properties are enough to find the entire state. So state 1 is found. State 2 is simply isentropic, and the pressure is the pressure of the boiler, isentropic to state 1, so S2 equals S1. Of course, the mass flow rate doesn't change, and that produces our state 2. If we go to state 3, it is remember, it's the boiler exit, so it has the maximum temperature. T3 must be equal to Tmax, and the pressure is, of course, the same as boiler pressure. Look, I'm limiting my unknowns to, all the variables to the ones I declared, so it makes the problem solving much easier. If we go to the graphics panel, we expect state 1, if we draw a constant pressure line through state 1, it should go through so of course, state 1 will be the pressure is the condenser pressure. If we draw a line through pressure 2, a constant pressure line through state 2, it should take us from 2 to 2 to 3, just like as shown here. Okay. Now from 3 to 4, we have the first turbine. Again, the pressure at state 4 is not known, even though it's coming as green when you solve the problem first. And when you, if the state 5 is not known, this equation is not going to produce a pressure, obviously. So it will have a white background. Okay, it will have a white background that is waiting to be evaluated. But this is a valid equation. P4 is now declared in terms of the next state, P5. And of course, it's isentropic. So we give the isentropic condition and mass flow rate. And this state will not be calculated completely for the reason I the reason I described, because P4 is not known yet. So you go to state 5, which is the reheat exit. Reheat exit has the same temperature, the maximum temperature, and of course we don't know the pressure, but we do know that, of course, we cannot say pressure equals same as P4 because we declared P4 in terms of P5. A circular definition will not work, obviously. So we need something else. And the clue is that it's isentropic. State 5 is isentropic to state 6. So we are using this. Again, we don't know state 6. So this state is also not going to be evaluated because entropy is not known. Only temperature is known. And of course, the mass flow rate is known. So 5 and 6, state 4 and state 5 are not completely evaluated yet. So when you go to state 6, which is the second turbine exit, the low pressure exit, and we know the quality is X exit 0.9. So the quality is known, and also we know at the exit of the second turbine, the pressure might be same as the condenser pressure. So now we know sufficient input conditions, sufficient independent properties to calculate the state completely. Obviously, now we can go back and calculate state 5 and then go back state 4, or we could just click super calculate and immediately iterate and calculate all states for you. When you go to the device panel, now that all the states are ready, of course you can go to the graphics panel and you can show that there are 3 different pressure. Okay, this is the condenser pressure, and this is the boiler pressure, and the state, the state 4 is goes to the reheat. So these are the 3 different pressures in this problem, and the reheat pressure has been found for us. We can go to state 4 or 5 to pick up the answer. So if you go to state 4 or 5, the reheat pressure is 5259 kPa or 5.26 MPa. In the device panel, again, it's very standard. The device 1 is our pump. It operates between state 1 and 2, and heat transfer is 0, so pump work is found. Device 2 is the boiler, again 2 to 3, and as you can see, this is 0, there is no work, and therefore heat transfer is found. We go to device 3, and device 3 is our turbine. So as you can see, it operates between 3 and 4. It's the high pressure turbine, so work is found, heat transfer is 0. Device 4 is the reheater, so therefore it operates between 4 and 5. There's no work transfer, and the heat transfer of reheat is found. So the heat added in the cycle is the heat added in the boiler and in the reheater. The device 5 is our second turbine, so therefore heat transfer is 0. It operates between 5 and 6. Pretty simple. Energy equation is solved, and W dot external 5 is calculated. Device 6 is the condenser, so it goes from 6 back to 1, takes us back to 1, the saturated liquid exit. And state 6 is the one, remember, where the quality must be 90%, and that gives us the heat transfer in the condenser, which must be negative because heat is lost. In the cycle panel, these are all put together, and we come up with all the relevant answer in the problem. Suppose what is the thermal efficiency, etc. Or suppose what is the net power, which must be same as the net heat in. So suppose you want to do a parametric study now. So let's write down this number so that we can compare. Performance of a power plant is basically you take a look at thermal efficiency and the net power, 1694. Now suppose we want to do a quick parametric study in which we say, okay, what if we change the exit quality of this problem. Suppose instead of 0.9, we say, okay, we take it to 1. Second, okay, that is quality is 1 means saturated, saturated exit condition. We do a calculate and we do a super calculate. That's it. So if you can go to the graphics panel, state 6 should be saturated now, as you can see. And if you come to the cycle panel, all the quantities have been evaluated. You can see that the results are not good because of this increasing the quality. What we got is lower net work, net power, and also we got lower efficiency.